This is my talk. I have this feature that I'm able to talk for 2 or 3 hours without stopping. So if you don't make any questions, believe me, I will talk for 2 hours without stopping. So I strongly advise you to find out some questions in the middle to interrupt me. All right, this is my email down here. If you have any question later, please address them to me. And the title of the talk, as you can see, is in the west of deadlocks and atomicity violations. And basically, this is our schedule for the next 1.5 hours or almost 2 hours. So we will speak a bit about why are we here, and then what are these things as anomalies. Maybe it's familiar for some of you, maybe it's not familiar for all of you. And then we'll go to this topic, which means to understand what is something being wrong, we need first to understand what does it mean to be right. So we will assign semantics to concurrent programs, and then we'll talk about different types of errors. And depending on how fast I go, I will go a bit further or a bit, I will stop a bit earlier on the detection of errors. So first question, why are we here today? Well, not today, but why are we here actually today? Me listening or talking about detection of atomicity violations and concurrency errors in general? Well, the answer is very easy. It's Moore's fault, right? In the past, maybe until 2005, more or less, processors were getting faster and faster and faster and faster. So basically, you get more transistors in processors, and the transistors would allow the processors to go faster. And life was great. Oops, life was great until we get this point in time, 2005, where the heat dissipation was too much, and basically the number of transistors kept on growing and growing, but not for speed. So basically, they went for quantity, and they start doubling the number of computational units inside the processor. So we went multicore. And the question is there a problem? And the answer is, well, to make use of the multiple cores, we need multiple operating processes. So we need multiple processes, and they need to interact with each other and somehow collaborate with each other. And the next question is, well, but is there a problem? And the answer is yes. All right? There is a huge problem with this concept. And so let's see now why there is a problem with this concept. Let's imagine this nice sequential program. And a sequential program is kind of a set of stages, very well-defined stages. So the program goes from the first stage to the second stage, third stage, fourth stage, and so on. And if, for example, at a certain point you find out that something is wrong, what you do is basically you go backwards. And you go backwards either by re-executing up to that point, or if you use a decent debugger, actually you can execute the program backwards. And in the end, you analyze the previous state, you look for the problem there. If the problem is there, great. If the problem is not there, you go a bit more backward until you find the situation. The thing is that the program is deterministic, and if you start it from the beginning, you get exactly the same set of states. So if you find a bug, you re-execute the program, and you find the bug again. So what happens if we have multiple processes? Well, the multiple processes are running and somehow collaborating, and life is great, and everything is beautiful, until you notice that some of them are not really, really doing what everyone is expecting. And when you get to this point, the question is, who's the fault? Where? Will I get the processes backwards? Each process is going backwards until which point? So it's not the same stuff. And so dealing with concurrency errors is a different world from dealing with sequential errors. So going a bit more technical, although not too much, let's see why there is this problem of synchronization in between multiple processes accessing shared resources. So I have here this beautiful blue chewing gum. And this beautiful blue chewing gum is desired by these 4 things, whatever. And the 4 things are really desiring the chewing gum, but they have a problem. They desire the chewing gum to be the same color as they are. So this is the rule, easy. So green is saying, oh, I would love this chewing gum to be green. And what does green do? Well, green paints the chewing gum green, and now green is happy. The problem is that, well, yellow and orange are still there, and they're still thinking about painting the chewing gum. And as the same way as green did it, well, they try to do it. What is the result? Something like this. And this is a problem, because the final state for the chewing gum is not a valid state. It's not a full color. So basically, if you have a shared resource and you have concurrent accesses to the shared resource and synchronized, you may lend the shared resource to an invalid state. An invalid state means a bug. So this means your program is wrong, doing wrong stuff, so you have to fix your program. How do you fix your program? Well, this is what we call a data race. How do you fix your program? Well, you use logs, right? And now life is much easier because our chewing gum is green, and now because yellow and orange, they are well behaved, they will try to ask for the log before they paint the chewing gum. And when they do it at the same time, there is the semantics associated with the log, which means just one of them will get it. In this example, orange gets it first. So yellow has to wait. The operation doesn't fail for yellow. Yellow just is waiting for the log to be available, and orange gets the log. So orange now paints the chewing gum and releases the log. And when the log is released, it's changed automatically to yellow, which gets the log, paints the log, and yay, done. So what were the states that, although this operation and this operation, the orange and yellow operations were kind of executed at the same time, tentatively, they were somehow serialized one after the other. So the sequence we got was initially from blue, then to green, then orange, and then yellow. So although we had parallel operations going on, attempting to go on the resource, we had a very clear sequential execution of states, always well defined. This means sequential consistency. Although the program is concurrent, the behavior is the same as if the concurrent operations were executed one at a time. This is more or less informal definition for this concept. So, but is this the only possible final result? No, yeah. Let's go back to the green state, and when they are competing for the log, yellow can get it, right? If yellow gets it, paints yellow, then orange gets it, paints orange, and the sequence is a different sequence. Is this a valid sequence? Does it mean that the program is wrong? No. Perfect. Because if this is not a valid sequence, then the program has to force orange to go before yellow, or yellow before orange to go in the right order. If the program allows orange and yellow to try at the same time, this means that both results are acceptable. So this means that a concurrent program may have more than one correct result in the end of the execution. So this is also sequential consistency. It's sequentially consistent. So basically, these are the 3 stories that we had. These were the operations, and basically we had the green operation with these 2 operations going on the same time. And basically we got in our example, 3 different results. And the first 2, or the very first one, was inconsistent because the final state was not valid. The next 2 were consistent with the sequential concept, so they are all right. So our quest is kind of try to find situations where this stuff happens. Things can get a bit more messy if instead of having one resource, we have multiple resources and multiple collaborating processes. Because now, how do we solve this? Easy, very easy. We define a big law to rule them all, right? And if you do something like this, the world is great. But, well, it doesn't. You just sequentialize your process, so you're not using the multiple ORs anymore. If you want to use the multiple ORs, you have to have multiple laws in the resources. And when you go to this world, you get all kind of nasty stuff going on going wrong in your programs. So, let's, as I said, let's try to understand what does it mean for this thing of sequential consistency now in a more, let's say, more programming-oriented way. So let's assume we have this program, and this program has two shared variables, x and y, and they are both 0 in the very beginning. And although the colors are, this is blue, this is green, I hope you can see it, blue and green. It's not that clear. Things always go different from the computer screen to the projector. And now the question is, what are the final values for x, y? If I try to run this program and this program at the same time, what are the final values for x, y, a, and b? And I think everybody agrees that the final values for x and y are 1 and 2. What about a and b? Possible final values for a and b? 0? Both 0? Plus 0, 1? All right. It's not very well. It depends on the interleaving. So if we assume that this operation is atomic, it doesn't have to be, but let's assume it is. If we assume that these operations are atomic, it still depends on whether they are executed these two first and these two first and these two afterwards, or if you mix them. So let's see it in a different way, which means here, first the blue, then the green. And the final result is 2, 1. If you do first blue, 2 green, second blue, the final result is 0, 1. And if you do all the combinations, you get the next combination, you get 0, 1, 0, 0, 0, 1, 0, 1. So basically, although the program is just a single program, you get 3 different types of results, 3 different results here. So this means that our program, are these results valid? They have to be, otherwise our program is wrong. But sequential consistency means that if you execute this in parallel with this one, you get the same result as if one of these computations occur sequentially. That's what it means, sequential consistency. And, well, although these examples may suggest, because we have 2 threads or 2 processes, and we have 3 different results, and we have something like 1, 2, 3, 4, 5, 6 different possible computations for these 2 programs. The question is, what if we have still 2 processes, but we have a few more states? And arrows here denote that this state depends on this state. For example, if this is a distributed program, this can be sending a message, this can be receiving a message. If this is a shared memory program, this can be a lot, and this can be a lot of the same lot. So basically, it means that this event depends on this event. And the question now is, how many different computations do we have? Well, let's try to understand what happens here. This lattice represents not the events, represents the states. So 0, 0 means neither this program nor this program have executed any instruction at all. When we go, for example, here to 1, 0, means that this program have executed event 1, process 1, executed event 1, and process 2 executed 0 events up to now, 0 instructions. So basically, I will show you an example of a possible execution of these 2 processes. So basically, they start in 0, 0, and then process 2 executes his first instruction, and then goes for the second instruction. Oh, this is slightly different color, not different enough. Hope you can see the difference. Can you? Yep, good. I don't from here. So, and then it goes for the next instruction. And it goes for the next instruction as well. In process 2, execute without process 1 executing, and process 2 execute event 4? Yeah. Is it allowed to execute event 5? No. Right. So, event 05 is not valid. State 05 is not valid. If my processes go to state 05, it means I have an error somewhere. So now process 1 may advance. And now, is it possible for process 2 to advance? No. So let's advance process 1 again, and let's advance process 1 again. And now, is it possible for 2 to advance? Now it is. So basically, we are here, and now if we advance the remaining of the steps, we end up go over there. Great. So this means end of the rightmost possible execution of process 1 and 2. And with rightmost, I mean process 2 advances as much as possible, and process 1 advances only if it has to advance for process 2 to be allowed to advance. And if we do the opposite exercise, which means find the leftmost execution, where process 1 advances as much as possible and process 2 just whenever necessary, we will get something like this, which is, is here. This is the leftmost execution. Basically, there are still some states here in the middle, and because we are, yes? No, these are the relevant states. Of course, in a real program, you may have intermediate states here, but these are the states that I'm considering relevant for my example. So these states are totally local, and these states somehow promote some interaction with the other process, but these are the states that for some reason, I thought they were relevant for my program. So these are states, yes. No, over there they are events. Here they are states that reflect these events. So, if you have the leftmost or the rightmost, you will have, this means that these states are also invalid, and this means these states, these green states, they are not in the boundaries, but they are still valid as well. So what does it mean to execute the program? Basically, it means, oh, by the way, if we assume we have 7 states here, or because we have nothing executed, event 1 was executed, event 2 was executed. So if we assume that this process has 7 states, from nothing to everything, and this one has 6 states, if we count the states here, we get 30 states. But the question is, how many runs, how many different runs with these 30 states? And, well, let's talk about a run. And basically, a run is something like this. It's a sequence of valid states that take me from the initial state to the final state. So this is a possible run. And I will paint another one over this one, and this is a different run. And this is a different run. And I just played with these states here and some small change here. And I can play with all these states and all the variations. So basically, although I have something like 30 states here, I have zillions of different runs. And is this a problem? Well, if my bug is here, only the runs that drive my program to this point will actually trigger the bug. So if I'm executing the program and I find a bug, I notice a bug, I try to execute the program, and it is possible that it goes some other way. Again and again and again and again until I go to the demo, and in the demo it will go here, of course. So the thing is, we must find a way to, as much as possible, explore the space state, and for this you can use testing techniques like noise injection, but you must also understand what is going on and what does it mean for a program to be here, which is a valid state, or here, which is an invalid state. So basically, what does it mean that our program has an error? Well, basically, we get to one of these states, which are invalid. So basically, our aim here is, let's identify these states. And these states can be triggered by different reasons. I will talk about basically 3 of them: data races, high-level data races, and deadlocks. So, yeah. Violation means violation of sequential consistency, yes. No, not necessarily. With deadlocks, you are not really violating the sequential consistency. You are just getting your program to stop progress. All right? Basically, violation means usually you have these properties like progress, and if you violate progress, you are not violating sequential consistency per se, but your program is still wrong. So these are a few examples of things that can go wrong in your program. Data races, you have ordering violations, you have unintended sharing, you have high-level atomicity violations, which is different from, well, different. Although they are somehow related to traditional data races, they are different stuff. And deadlocks. One of the interesting things here is that, come on. It was supposed to be some animation here for some reason, didn't show up. All right. So, oh no, yeah, I will come back to it later. All right, so let's see what is a data race. And basically you have a data race when if multiple processes are sharing some data, all right, and the final result is not sequentially consistent. So if we assume that we have this thread or this process, I will use the terms with the same meaning. This thread or this process is doing a deposit, and this one is doing a withdrawal. And if we assume that these operations are atomic, for example, the addition and the subtraction, so what happens here? Basically, what happens is that I may have this situation where first I execute instructions from withdrawal and then the instructions from deposit. And it's all right. This is sequentially consistent. Although even if I try to do them at the same time, if the final result for my program is the same as if I execute this first and then this, I have sequential consistency. So this is great. Works. So another alternative is if it happens like this. First the deposit and then the withdrawal is still sequentially consistent. So it's great. Well, what happens if the withdrawal goes in the middle of the deposit? Well, the behavior, the thing is that the withdrawal will not be reflected in the final balance. So this means this result is not sequentially consistent, means our program is wrong. We need to somehow enforce some stronger atomicity concept here for the program to be correct. And the same happens on the other way if the deposit goes in between the withdraw instructions, and in this case it's a deposit that is going to be lost. So either money shows up in the system, extra money, or it just disappears. So what about ordering violation? This is a very common error as well. Although in these examples these look as trivial, in real world if your program is more complex, this happens a lot as well. And you have an order violation when you are assuming that this instruction is going to be executed, finished before this instruction happens. So you create a thread and then you start a worker. The problem is if the thread over here somehow is consuming the work that you are going to start afterwards. So reality means, well, with a very, very high probability, this operation will kind of start something in the background. And if this is, let's say, a few instructions afterward, not immediately, this one, the thread will be created, but before the thread starts, really, you will create the object. So the object already exists when the thread really starts, because creating a thread has some overhead, management overhead for the virtual machine, if we have a virtual machine, or for the operating system otherwise. But sometimes, for some reason, especially if this is hidden in a more complex operation, or if this is a bit further down with some instructions in between, the thread may be ready and running before I initialize my object. And in this situation, the thread is consuming an invalid object. So this is what is usually called ordering violation, because you are just assuming that this operation will be executed and finished, and then this one will be executed and finished. But this operation actually starts a thread that is going to do stuff, and you are not sure when the thread starts doing the stuff. So this is another concept of unintended sharing. And in this is C-line, not Java-line, but I will mix the examples and the languages. And basically, I have this local variable in this function with the static keyword before. Do you know the impact of this static keyword? Who knows the impact of this static keyword here? Yeah. Exactly. Usually, local variables go to the stack, to this area of the program execution, which is the stack. And global variables go to the data segment instead of the stack segment. If you have a local variable with a static keyword before, then it goes to the data segment as well, which means that the variable will be created once, initialized once, and the value will persist from an invocation of the function to the next invocation. So basically, if I have two threads executing work, what will be the final? What will they print? $10 and $20, perfect. 10 and 20, not 10 and 10. Because the first one will initialize the variable, will print 10, but the second one, because the variable was already initialized, it will just add and print 20, and this is completely ignored. So, and of course, again, with this example, this is trivial. With more complex programs, this happens. So, let's speak about high-level data races. How many of you have heard about high-level data races? None? Oh, something new. Good. All right. So the concept for high-level data races is you are using logs. So all your accesses to the shared data is logs. So the problem is not the absence of logs. The problem is the scope of logs. All right? So the problem is not with being or not being logged, because everything is logged. The problem is, what are you accessing inside the log? So I will give you an example. We have this object, and this object has two fields, field 1 and field 2. And I have thread 1, which just runs, and is running. Thread 1 is red, and is running, and at a certain point, it stops, and it loads the object, and reads field 1. It unlocks the object and proceeds. A bit later, it wants to access field 2. It locks the object again, accesses field 2, and unlocks the object and proceeds. Just one lock in the object, but it accesses first field 1 and afterwards field 2 separately. Now we have thread 2, which does the same. Lock, access field 1, unlock, lock, access field 2, unlock. Is this right? Is there a problem here? Anyone sees a problem? Yeah? But up to now, yes, that's perfect. That's exactly the situation. But up to now, no, that's not really the problem. That problem only exists when we show thread 3 here. But that's exactly the problem. But we need thread 3 for this. And thread 3 does something different. It runs, and at a certain point, it locks the object, and it accesses both field 1 and field 2 under the same locking period. And then it proceeds. And now, yes. Because this accesses on the left, basically thread 1 and thread 2, they consider is that object fields are separate entities. I lock the object to access them, but they are separate entities. And thread 3 thinks that field 1 and field 2, they are somehow related entities because I lock them, I lock the object and I access it, both of them in the same lock. This means they are somehow related. Otherwise, because I want to have as much concurrency as possible, I would have lock access 1 and lock access 2 and lock. So if I do it in the same lock, this means that 3 believes that they are somehow related. And now I have that problem, yes. That sometimes these ones may see states that are not valid, and I will get back to this a bit later. Actually, this example shows how it happens, although I will come back to this example later. So this example is exactly this, all right, but with a Java thing. And the thing is we have this concept of a pair, which has two coordinates, x and y. And I have the get x, which returns the x coordinate. I have the get y, which returns the y coordinate, and they are synchronized. So I'm accessing the fields in synchronized state to get x and to get y. And I have a set pair, which with a single lock will write both of the fields. So basically this, and if I have like our thread 2 or thread 1 or thread 2 running these two separate accesses, and if I have thread 3 running this one, right, then I may have a problem. If they make some use of like this. And I will show you in a minute exactly the same example and the possible execution and why this leads to an invalid state, if it's not clear for you right now. So, deadlocks. Deadlocks are probably very familiar to all of you, but basically I have a deadlock. I will go back to the other example in a minute. Deadlocks are very familiar example, are familiar for you, but basically I have a deadlock when I have a thread that issues some operation, and I have another thread that issues an operation that somehow is incompatible with the first one, like acquiring a lock, and it has to wait. So, this didn't acquire, though this is the other. So basically these ones acquired A, this one acquired lock B, it's compatible, different locks. And now this one tries to get B, and it has to wait for the lock to be released. It's in the semantics of the lock. And then this one tries to acquire A, and now this one has to wait for this one to release. So basically they're waiting for each other, and we have this deadlock situation. We'll see how to handle them. Oh yeah, let's go back here. So these are the situations I've been describing lightly, and basically this is nice. Ordering violations and unintended sharing, usually the symptoms are more or less the same as data races. They are not really data races in the traditional sense, but the symptoms are similar. So basically let's hide them. I'm also hiding from the top live lots. How to deal with live lots is not here, but it's something interesting as well. Have you heard about live lots? Yes, yes, no? Okay. Live lots is, you have this important condition in a program. In a sequential program is more or less trivial, it will happen, which is progress. As the program executes, there will be some progress in the computation. When you have a deadlock, the program is not progressing anymore. Because at least two threads or two processes are waiting for each other, so they are not progressing, they are stopped. So basically they check, can I do this? No. So I will wait until someone tells me that I can do this. And they are both waiting for each other. Basically, you have a deadlock. The situation for the live lock is that they are, instead of being passive, waiting for the notification saying, oh, you may progress, you may go on, they are proactive and they try to do it. All right? And they are proactive, they try to do it, they fail, they go backwards. And they try to do it again. They fail, they go backwards. The example I usually give for this is if two people meet in a door where just one of them can pass. And if they are really very polite, one of them say, oh, please, after you. And the other one says, no, 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 please, after you. No, no, I insist, please, after you. No, no, after you. There is no progress. They are both stuck there. There is no progress, right? So if they are excessively polite, no progress. They are deadlocks. But instead of being excessively polite, if they are excessively rude, they will both try to pass at the same time. They will hit each other. They cannot pass. They will go back, both of them, and they will try again. And they will hit each other again. And they will go back again. And they will go forward again, hit each other again. So that's a lifelong. Instead of being just stopped, they are actively trying to progress, but for some reason they conflict, they withdraw, they go back, and they restart again. So, but basically, we'll take them out of the equation right now. So let's talk about data races. What does it mean that we have a data race? Basically, it means that we have two conflicting memory accesses happening happening concurrently. And for this definition, which may seem easy, we have two important concepts here. First of all, conflicting memory accesses. What does it mean for two memory accesses to be conflicting? And then we have happening concurrently, which is also important to be clear. So let's go to the first one. And the first one means we are accessing the same memory location. And so the two conflicting accesses are on the same memory location. And the second one is at least one of them is a write. Because if they are just observing, although it's on the same memory location, if they are just reading, they are not spoiling each other. So they can do it. So if for this to be a conflict, one of them has to be changing the variable, and the other one may also be changing or just reading. So what does it mean to happen concurrently? Well, two events or two instructions are concurrent if, let's say, the instructions A and B, if both outcomes, the outcome of A followed by B or B followed by A, are both valid for my program. So they correspond to sequentially consistent executions of my program. Let's go back to our example with X, Y, A, and B. So the question is, I think the answer is more or less obvious for you. Is X and Y concurrent instructions, operations? And because they are in the same program, and we expect the instructions in the program to be executed by the order that they show up. By the way, this is not always true, but that's what we expect. So we say more or less in a more empirical way, oh, they are not concurrent. But let's see a more methodological way to check this. So let's find all the occurrences of instruction A and all the occurrences of instruction B. And if B always comes after A, so there is always only one possible outcome, which is A followed by B. The opposite is not possible. So A and B are not concurrent executions, are not concurrent operations. So let's check A and C. If we look at A and C, in some situations I have A followed by C. In some others I have C followed by A. And because possible outcomes are possible, this means that A and C are concurrent operations. So, with I have a global shared variable X, initial value 0. And I have two threads running these operations, these loops. From 0 to 5, X equals X plus 1. And the question is, what are the possible final values for X? Possible answers. Any value between 2 and 10. Any value between 5 and 10, and always 10. Who votes in option A? No one. 1, 2. All right. Who votes in option B? 2, 3. Who votes in option C? No. All right. No one votes on option C. All right, so you know what is the right answer? Option 1. Why? Yep. I'm not sure with your line of thinking you would get 2. Maybe you are right in your mind, but your speech did not lead us to exactly to this situation, I think. Do you have any? Who else? Yes. Yeah, and then both read 1, both write 2, both read 2, both write 3. So you get 5 to 10, not 2 to 10. Yeah, so the thing is, sometimes some of the executions are really, really, really nasty. They never, ever, ever happen until the critical moment, like the Ariane 5, or the Mars rover, or this kind of problems, that you try the software hundreds of times, millions of times, you test it, you believe it's correct, and then in the right moment they fail because the nasty execution really happened. And the nasty execution usually happens in the demo. Do you know why? Because you are changing the execution conditions usually. You go to a different setup with a different network, with a different computer, with more cores, less cores, faster, slower, different operating system, different version of the compiler, whatever. You are changing the execution situation, and you are going, instead of going by one of the runs, you just select the other, it just goes on the other run where is the bug. So, how do we get 2 to 10? I will give you the example for 2, and then it's easy to guess for the other values, all right? So, we have here S, we have A and B, and basically what it happens is that A reads 0. Perfect. And A remains to 1, but before A stores 1, as you are expecting, B will read 0. And B stores 1. I mean, B remains to 1, and now B stores 1. Right? And now B will do this. And B will remain to 2, and to 3, and to 4. And now comes the nasty part. B doesn't do the last operation. Now there is a context switch, and we go back here. And here A is gonna. You remember this is 4. B is missing 1, right? So A is in the first one. So A stores 1. And you are expecting A to progress. This is the nasty interleaving. So A does nothing, and B reads 1. And B goes for 2, but doesn't store, holding its last operation from B. Now A does all the remaining operations. So A goes for 2, for 3, 4, and 5. A is done. And now 2 is finishing. Yay! 2. Not trivial. So doing concurrent programs is not the same as doing sequential programs. You have to anticipate these kind of problems, and you have to be sure that they don't happen in your final solution. So, we already know what it means to have a program that is violating the sequential semantics and the sequential consistency. And now the question is how to monitor this stuff, how to work with this. How will we detect these bugs? Well, you may go on two main approaches. One of them is static analysis. Basically, with static analysis, it means you are not really executing your program, right? You are just looking at the program, looking at the source code, or looking at some representation of the program. You have another program, usually, that looks at the original program and somehow tries to infer properties, guess properties, detect properties in the original program without executing it. Advantages for static analysis. Well, because you are not really executing the program, you can somehow reason about all the possible inputs at the same time. So if there is a variable of type integer, you can just assume it's a variable of type integer in your checking, and not that the variable has the value 2, the value 5, or the value 25. And just say it's an integer, and it's violating some property of this integer later. There is no runtime overhead, because this analysis is done before the program is executed. So there is no runtime overhead. If the program is correct, you just run the program, and it's all right. Of course, it applies very well-defined methodologies. Of course, people are always inventing new stuff here. There is lots of research always going on this topic. But there is very well-defined methodologies for doing static analysis, and you can get important stuff out of this, important results out of this. And one of the main problems is that usually your program has to be annotated with additional information. So for you to have a good static analysis, you have to increment your program, like Wolfgang was lecturing yesterday, I think it was yesterday, about with JML. You have to add all those annotations, trying to tell the analyzer what is the expected semantic for your program, so that it can confront the expected semantics with the observed semantics from the analysis. And of course, annotating a program means you have to have an expert, and you have to annotate it right, and that means it's expensive. Well, you have tools that work over here. Disadvantages of static analysis, by the way. Well, these tools usually produce false positives and false negatives. False positives means there is an error there, and I didn't find it. Because it's easy for the error to be masked by something else. Because you are doing static analysis, and if you have an evaluation to the operating system, you don't know what is done down there. So you are just assuming that everything stays the same, for example, and the operating system may change something. So basically, the operating system or whatever is the method from a library from which you don't have the source code, you are just evoking this method, you don't have the source code, it returns, you are assuming that this method is not changing your program state, and it does. So basically, you may step into a bug, and you don't detect it because you are not able to analyze everything in your program. So you have to do some assumptions about the behavior of some methods because you don't have the source code, you don't have access to the specification for those instructions. And they have also false negatives. Why? Because usually these are complex properties, and sometimes the properties are how do you say in English? Decidival, computable. And so you do some kind of an over approximation. And when you do this over approximation, what you get is, if you do an over approximation, your analysis will trigger an error, but the error is the result of the over approximation and not of the real problem. So basically, what you get is the alarm for an error, and the real program doesn't have this error. That's a false negative. Oh, sorry, it's the opposite. The other way, false positives and false negatives. False positives are the errors announced that are not real errors, and false negatives are errors that are missed. Sorry. Again, requiring programmer annotations is expensive. Usually, you produce lots. These kind of tools produce lots and lots of huge reports, and you have to somehow a human frequently has to read these reports and process them, and that's also tiring and expensive. And if you have too many false positives, then you have hundreds of alarms, and just 1 or 2 are real, and very easily you will skip these 1 or 2, you will miss these 1 or 2 that are real. So basically this is hard stuff. And if the program is too complex, or the properties you want to check are too complex as well, frequently static analysis doesn't scale. So the alternative is, let's go to dynamic analysis. So what do? Basically, you run the program, and you observe the state of the program while it is running. How do you observe? Well, you use AspectJ to monitor, you use whatever tools, you use a debugger, you use whatever tool there is for monitoring your program and generating events, relevant events for your program. And if you do this, well, what are the advantages? Well, first of all, soundness. Soundness in the sense that every actual data race reported is real. Sorry, that's here. That it reports all the data races. I mean, you can detect all the data races, but this soundness is relative, because it detects all the data races in the run that you observed. It will not detect the data races in the other runs that you did not observe. So the soundness here is a relative soundness. It's for the observed run, if there is a data race, you will detect it. And also, it's easier to be complete in the sense that if you give up an alarm, it's a real data race. So what's the problem with dynamic analysis? Well, you are observing the program while it is running, so it goes much slower. And if this is a long time running program, it may be an invalid option. And then usually you have to keep lots of information about the past, what happened in the past, for you to know what is happening in the other threads, in the past of the other threads, for you to detect data races. So sometimes the memory overhead for keeping the state of the program is too much. And reasoning only about the observed executions means you may be missing errors in the alternative paths for the other runs, possible runs. So either with static analysis or dynamic analysis, how do you detect a data race? Well, you can do it by, using the happens before relation from Lamport. You have heard about this, right? For sure. So let's see how it works. First of all, let's define what is a lot. A lot is an object, and basically it has 2 operations, lot and unlot. And acquiring a lot is only it only returns if the object is unlocked. If the lot is locked and I try to acquire it, I will wait for the lot to be released. So what does it mean, something that happens before something else? Well, in a single-threaded program, the instructions are supposedly executed by the order they show up in our program. So basically, the programming order also reflects the happens before order. If we have multiple threads, and there is a long speech here with A and B, but it's much easier to read it here. If I have 2 threads, and if operation A is unlocked and operation B is locked over the same object, and they happen in this order, then A happens before B, because this operation lock only returns after the lock is unlocked here. So A happens before B because first there is the unlock operation, and then afterwards there is the lock operation. Although they are in different threads, they are somehow related to each other, and I can map a happens before relation from one thread to the next thread. So if I have a violation of the happens before, it is possible that I have a data race. It doesn't mean that I have a data race, it means that it is possible that I have a data race. Let's see an example. So we have lock, increment x, and lock on thread 1. On thread 2, we have lock, increment x, and then lock. Well, I'm using here a visual representation trying to mean that this is executed before this one, all right? Although they are running at the same time currently. So, and what I know is that because this is the program order, I know that lot happens before the increment. And I know the increment happens before unlock. And I have exactly the same relation here. So all this, the next instruction, the previous instruction happens before the next instruction. Now the question is, in a map, have a happen before relation between events from thread 1 to thread 2? And the answer is yes. If first this thread unlocks and then this thread locks, then the unlock operation happens before this lock operation. And the question is, let's give some numbers here. And what do I know? As I was saying, event 1 happens before event 2, which happens before event 3. So by transitivity, event 1 happens before event 3, of course. This is a transitive property. And I can say the same here. And I can also say that event 3 happens before event 7. And by transitivity, I can say that event 2 happens before event 8. So basically, there are no data races in this program because there was no violation of the property. Yes? Yes? Yeah, it represents timestamps. Well, let's assume these were timestamps. So let's assume you have a monitor, and when this instruction was executed, it was sent to the monitor. So it was the first one. And then this one was sent to the monitor, second one. This one was sent afterwards. So some others were sent afterwards, I don't know which ones. And then the monitor received this one, and then this one, and then this one. So you know that in the real execution, this happens after this one. All right? So the question is, would it be possible to have a data race here? And the answer is, with this execution, with this observation, no. But if we have another operation here, which is y equal increment y, and we observe this, which is very similar to the previous one, the question is, we already know, look, incrementing y is outside of the law. And the question is it safe to increment y outside of the law? If our execution is something like this, so basically we observe these events first, and then these events afterwards, as in the previous example. All right, so what we have is that, what we know is that this happens before the law, right? And before the increment, and before this one. So this increment happens before the unlock. And we know the unlock happens before this lock. And we know this lock happens before this increment. So we know that in this run, this increment can never go in parallel with this one and mess up the memory state. So this run was safe. The question is, do we have a bug in this program? Is it possible to have a different run, in this lattice, a different path in this lattice, which leads to a buggy state? And the answer is yes. If the execution is something like this, where this one goes first and this one goes a bit afterwards, what we have is that this unlock is before this lock. So again, I know that this increment on x is before this increment on x. So x, the accesses to x are always ordered by this happens before relation. But the question is about this y here. I have no information about this y. This increment can go in parallel with this one. And I have a bug. So what is the problem with happens before? Is that if in my testing I go into this run instead of the other one, I will say my program is perfect. So it's sensitive. It's very sensitive to the overage of the branches of the interleavings. If I go to this one, I will say I have a problem here. So happens before is great or it's good, but it's really dependent on, it's really sensitive to the overage of the interleavings, of possible interleavings of our programs. And in the lattice example, you have seen with just 2 processes and a few states, the number of different interleavings I had. And it was just 2 processes. If you have 3 processes, I don't know if you notice, but instead of being a 2-dimensional lattice, we would go somehow 3-dimensional. And with 4 processes, we go 4 dimensions. So the state explosion is incredible. So frequently it's not possible to over them all. And so you may always have these latent bugs. So how do we solve this? How do we address this? Well, let's summarize. Happens before defines a partial order relation for the events. And data races are possible if we find 2 events that do not observe this property of partial ordering. But is very sensitive. Happens before is very sensitive to the overage of the interleavings during testing. So let's talk about a different algorithm which is insensitive to this in this aspect. All right. So just to reinforce that usually there are multiple approaches to address the same problem with different results. So the lot set algorithm, that was proposed in a tool named Eraser some years ago, basically it's not looking for deadlocks. It's checking if the program has a consistent locking discipline. And if it does, it's a sufficient condition to say it's deadlock free. What does this mean? Means that if the program verifies this property, If the program fails on this property, you don't know nothing about this one, right? If it doesn't use a consistent locking discipline, it may or may not have a data race. We don't know. But if it has a consistent locking discipline, then it's data race free. So how does it work? Did we have a consistent locking discipline in this example of the bank? That means that all the accesses to the shared variables were protected by the same lock, by at least one lock. And here we have this lock which was named balanced lock and then lock in the right position, lock and lock in the right position. Yay, we did use a consistent locking discipline. All right, let's see another example. How do we detect this? Let's see another example. I have wire A, B, increment X, release B, A, wire A, C, increment X, release C, A. Am I using a consistent locking discipline? The meaning is all the accesses to the variable X are always protected by the same lock, always protected by one lock, and it's always the same. Well, if we look here, in the first example, we say if we look here, we may kind of guess. Well, access to X is protected by either A, B, or by both of them, right? But when you look down here, you'll say, oh, accesses to X are protected by either B, C, or both of them. So intuitively, what we guess from here that X is protected by B, right? Because A is not being used here, so it's not protecting X. C is not being used here, it's not protecting X. So, but B is being used in both. So yes, although I'm acquiring more locks than necessary, I'm using a consistent locking discipline because I'm verifying this property that all the accesses to the shared data are protected by one lock, and this lock is always the same, by at least one lock, and this lock is always the same one. So, how can we get this from a program? Well, we can use the lock set algorithm. And lock set algorithm basically follows these steps. For each shared data item, we will try to infer, to guess which lock is protecting this data item by looking at the program. It can be by static analysis or by monitoring, dynamic analysis. You can apply this algorithm in both approaches. But we will try to guess which lot is really protecting this shared data item. And for this, we need two sets, the lots held and the lot set. And the lots held means which lots was I holding when I accessed the variable. And the lot set basically says, so this is the end of another set, this is a superset. Lot set starts with all the lots, and I'm going to remove lots from there that are not possible to be protecting my variable. And basically, these are the how you operate with it. When you acquire a lot L, you just add it to the lots held. If I acquire a new lot, I will add it to this set, lots held. And if I release a lot, I will remove it from the lots held. And now, every time I access the variable, I will update the lot set with the intersection between the current state of lot set and the lots held. Let's see an example. If the lot set becomes empty, means if the lot set, which lot set is the set of lots that are possibly protecting my variable. So if it becomes empty, means none. An alarm should be raised. Does it mean that I have a data race? No. It means that I have a possible data race. But if it never becomes empty, then I have no data race. So let's see an example. I have this short program over there, and I have the lots held initialized to empty. I have the lot set initialized to the set of all lots. So when I execute the first operation, which is get a lot, what I do is add the lot to the lot set. And this one stays the same. So next operation is a lot M2. So I will add M2 to the lot set, and to the lots held, lot set stays the same. Next operation is access the variable. When I access the variable, what I do is the lot set will be the intersection of this set with this set. So the new lot set is intersection of the new lots held is intersection of the previous value of lots held. Sorry, the new lot set is intersection of the lots held with the previous lot set. So I have actually the intersection is the same set. So this, what does this mean? This means that M1 and M2, I was holding M1 and M2 when I accessed the variable, and both M1 and M2 are good candidates for this concept of this lot is protecting this variable. So let's proceed a bit more, and I'm unlocking M2, so the lot set stays, and now I will remove M2 from the lots held. Next step, I'm accessing V again. Wait, now there's something new. Because when I access V again, I will intersect M2 with my current lot set, my current lots held with the lot set. And now M2, I know that M2 is not protecting the variable for sure. It's intuitive because I'm accessing V outside of the lot of the scope of lot 2. So basically, it's removed from the lot set. And if I proceed, now I'm wiring M1. Sorry, I'm releasing M1, and now I'm wiring M2. And what I know, this set only reduces; it never increases. Although here the set may have less elements and then more elements as I wire and release lots. The lot set will start with the universals, with the set of all the lots, and will just decrease, always, until you have possibly 0. If you don't get 0, means this lot is, up to this point, this lot is protecting the variable. If you get to the empty set, it means no lot is really protecting the variable. So when I get here, I add M2 to the lots held, and now when I'm accessing V again, I will do the intersection of M2, which is the lot I'm holding, with my lot set, which is M1. And I get empty set. And this means, oh, oops, an alarm. Does it mean I have a data race? Not necessarily. It means I have a potential data race. It requires further analysis. In this case, I really had a data race, all right, a real data race. But sometimes this algorithm fails. Fails in the sense that it gives you a false positive. It gives you an alarm, and the program really doesn't have a data race. I think I have an example here. So no warnings, no data race. Warning, maybe there is a data race. But actually what a warning means is you have a bad locking discipline. And a bad locking discipline may lead or not to data races. Yeah, let's see the example here. I have X, and I have a wire M1, M2, and here I have M2, M3, and here I have M1, M3. So if I execute this with lot set, will it trigger an alarm or not? Intuitively. Well, if I look here, I would say both M1 and M2 may be protecting my variable, right? But if I look here, I would say M2 and M3, right? If I intercept the sets, it would mean just M2. M1 is not protecting, right? And now, if I move here, I had just M2. And if I move here, I have M1 and M3. M2 is not here. So, alarm. Bad locking discipline. Now the question is it ever possible for two increment operations running at the same time with this program? And the answer is no. Because this one is synchronized with this one on M2. This one is synchronized with this one on M1. And this one is synchronized with this one on M3. So you never get a data race here. But still you are using a very weird locking discipline. So the program sets an alarm. The algorithm sets an alarm. Oh. How are we? Half an hour. Good. So, let's talk about high-level data races. And how do we detect high-level data races? Let's go back to our example. Okay. If you look at the set of atomicity violations, you get what we were talking before, which is traditionally named data races, or low-level data races by opposition to high-level data races. You got the concept before. There's also stale values, which I skipped from the list, right? And remember, high-level data races, you remember the example. And these threads assuming that field 1 and field 2 were separate entities. And this thread assuming that field 1 and field 2, they were somehow correlative. And I've shown you an example, which was this example, where I have a set pair, which in a synchronized concept on text sets both X and Y. And I had these equals, which would access this get X and get Y, and get X and get Y themselves were synchronized. Although the equals itself was not, the get X and the get Y were synchronized. So if I have thread 1 executing this, and thread 1 executing this, look, all the accesses to X are always protected. Here they are protected in this operation, and here they are protected in this operation here. The same for Y, so all the accesses are protected. And if my variable, the initial state is, let's say, X and Y are 1, 1, and I have thread 1 running this, and thread 2 is running this. And thread 2 is atomically changing the state from 1, 1 to 2, 2. So what are the sequentially consistent results for this program? What will thread 1, are X and Y always equal or not? Look, if this thread runs and this thread runs, what am I expecting to happen? That's the question. What is the semantic for my program? I have one thread checking if x equals y, and I have another thread atomically changing x and y from 1, 1 to 2, 2. So the thread that is observing should observe either 1, 1, and you would say they are equal, or will observe 2, 2. Depends on whether it goes before or after that one. And it will say as well, they are equal. So the question is it possible for thread 1 to observe something else that was never really the state of the program? And the thing is, if the first instruction of this thread is executed, it synchronizes. So it will read 1. Doesn't know about y, it's going to get y in a while, in the next operation. But if the execution is stopped and interleaving changes here, this one will change the state from 1, 1 to 2, 2 atomically. And now this one goes and gets y in the synchronized context as well, always protected. And it gets 2. So the observation actually was 1, 2. And this was never, ever the state of the pair. The pair was changed atomically from 1, 1 to 1 to 2, 2. But actually there is an observer here that although all the accesses were protected by locks, observers a state which was never the real state for my pair. So this is a high-level data race. And the question is, how do I detect this? Again, I can do this statically or dynamically. All right, so I'm not forcing very much. I'm speaking about how to do it, not really how to do the operational part of monitoring the programs or analyzing the programs. That can be studied elsewhere. So how do we detect this? For this, we have to resort to this concept of a view. And the view is the set of variables that were accessed inside an atomic region, inside the synchronized block. The set of global variables, of shared variables. And basically, we can speak about the read view and the write view. Is a subset of the read operations and the write operations. All right? So the view is the set of all variables, and the read view is the set of all variables that were read, and the write view is the set of all variables that were written. So it's just an optimization, but we can work with the concept of view in general. So basically, let's see this example, and if I have this example, how do I construct or how do I build the view of the variables for this example? Well, it would have been better if I had done with the previous one. I didn't, so let's work with this one. This one, basically, I have this method, and this method, which is synchronized, is also this other method, which is not synchronized. But because this method is being invoked in the context of a synchronized method, it's also executed under the same law. So what is the view for this? Basically, the view for this method is the set of shared variables that are accessed inside this method, or inside the methods that this method holds. So the set of global variables accessed in the increment x method are, I start with the empty set, and now when I look at the first operation, all is also ignore it, but I'm reading x, right? I'm accessing x. So read x. And then I'm invoking this other method, which although it's not synchronized again because it's invoked in this synchronized context. Sorry, this should be synchronized. Sorry, my mistake. Because it's being invoked in this synchronized context. It's also being considered. So basically, it's the set of variables accessed here plus the set of variables accessed here. And the set of variables accessed here are a write to x. So basically, yeah, a write to x. So basically, if I kind of join these all together, my set of variables is I read x and I write x. So my read set would be x, and my write set would be x. The same variable, but for different reasons. Now, what do I do with this? I have to do some data dependency analysis. And to understand this, let's go to this example. If I have something like x equals y, it means that x is depending on y. The value of x depends on y. And if I do x equals 2, I'm just changing x. And then if I do z equals x, it means that x depends on z. And I have this example to tell you that data dependency analysis is not trivial. It's not that complicated, but it's not trivial. Because by transitivity, I would assume that z depends on y. And it doesn't. Because x was changed to an independent value in the middle. So basically, we can go and assume that we have two x's, variable renaming, and this x, the first x depends on this y, and the z depends on the second x, because it's, if I change here x for w and here x for w, the program would be exactly the same and the dependency goes away. That's what I'm trying to mean with these h1 and h2 here, different x's. And in this case, the analysis is right, and I'm not wrongly assuming that z is depending on y. So this is data dependency, and we have to follow and trigger and understand all the dependencies between variables. Because when you set a variable to the value of some other, and if you are occupying the variable, and data races may affect, you may have data races on the new value. So, are there enough data dependencies? And the answer is no. You also have to consider control dependencies. And if I have this example, quickly, I have the parameters, and x1 depends on the first parameter. So, parameter is whatever is set to x1. Second parameter is set to x2. So, and then I have here a Boolean condition, and I have a value. The access to value depends on the state of the Boolean condition, and value is returned. And basically, I need to understand also the dependencies, the control flow, when the control flow depends on shared variables. And with both of these analyses, I can merge them together and kind of build the causal dependency graph, which somehow reflects both data and control dependencies. And then I can work here, and with the views and the data dependency analysis, I can understand whether I have or not a high-level data race. So why do I need this data dependency analysis? Yes? Yeah. All right. Depends on the level of analysis you want and the precision you want. If you do intra-procedural, it's much easier, of course. But it's possible that you will not find all the bugs. Although, it depends also on the logging discipline that you use. If you use synchronize it, for example, it has always to be intra-procedural. If you use explicit logging and unlocking, then you can do the lock in one place and the unlock in some elsewhere. So you have to go inter-procedural. So it depends. The level of analysis you go depends on the precision you want and on the logging discipline that you are using. Yep. So let's go here and let's define this concept, which is a direct correlation. Two variables are directly correlated if in the dependency graph I have a path from variable 1 to variable 2, then I would say that this variable depends on this variable. They have a direct correlation. The concept is rather easy. This one is a little bit more complex. We would say that two variables are common or related, and in this case is x1 and x2. If there is a third variable, z, that is written, and there is a path from x1 to z and from x2 to z. In this case, we say that these two variables are common or related. And why do we need this concept? To reduce the number of false positives, basically. This concept allows us to eliminate some false positives, some alarms that really don't correspond to high-level data races. So if we don't use this concept, you just get some more false positives. So how do we work with these now? Well, let's go back to this example. We have the set pair and the equals, and let's see, you remember we had this high-level data race, right? So let's see how it happens. So I will build the views, and the views, as I said, are the set of variables accesses in my methods. And I'm building the write view for set pair and the read view for set pair. Frequently already also the write set and the read set, right? So the write set or the write view is xy because I write xy and I read none of them. And here I will build the write and read views for get x and for get y. And both have something in the read and the write is empty. Now, what is the algorithm? I have this concept of a maximal view for a thread. A maximal view for a thread is a view that is not a subset of any other view. So, because this one has just one thread, it has one maximal view, which is this one. No, sorry, because this one has just one view, this view is necessarily maximal thread because it's unique. I'm speaking about the write views and read views separately. And if I go here, this thread has two read views. Both have, they are different, so this one is not included in this one, and this one is not included in this one. So they are both maximal views for thread 2. All right? But if this one was x and this one was xy, then I would have just one maximal which was xy because this one was included in this one. So the maximal means it's a superset of all the other threads, of all the other views. So what we do to detect if we have a high-level data race, we will kind of try to match these views from one thread. Views from one thread doesn't have to be maximal views. These ones are maximal by accident. They don't have to be maximal with the maximal views from the other thread. So basically, because this is a write, we will get either both here reads and writes, but the writes are empty, so we will get just reads. And what I do is the algorithm is the following. First of all, I will take the maximal view from thread 1 and I will intercept it with all the views from thread 2. And so I will intercept it with x and xy intersection with x, I get x. I will do the same and for the maximal view from thread 1 with the second view from thread 2, and I get y. And now I have a high-level data race if the results of the intersection do not form an inclusion chain, which means because x is not a subset of y, neither y is a subset of x, then I have a high-level data race. And now, to reduce the number of false positives, because this is a possible high-level data race, if I apply here the common correlation, the question is, I have a high-level data race if this is true, and they share this relation of being a common correlation. Otherwise, even if this is true and this is not true, I don't have a high-level data race. So let's see an example. Assume that, a more complex example, assume that I have a thread 1 which produces two views, two synchronized blocks. And in the first synchronized block, it reads A, B, and C. And in the second synchronized block, it reads A, B, C, and D. So V2 is a maximal view. V1 is not a maximal view because it's a subset of the second one. So I have another thread, and the other thread also produces two views, two synchronized blocks. In one of them I have A, B, E, and in the other one I have B, C, F. I'm not differentiating between read and write operations to make it easier. All right? Let's assume all of them were write operations. And now the question is, do we have a high-level data race? And to know if we have a high-level data race, we have just to apply the same concept. So let's take the maximal view from V1 and intercept it with all the views from T2. And if we don't find a data race in this situation, we have to do the opposite. Find the maximal views in T2 and insert them with all the views from T1. So let's start from T1. So V2 is a maximal view. Let's ignore V1. So now I will confront V2 with V3 and V4. So let's do the intersection. V2 with V3, and I get AB. And if I do the intersection of if I do the intersection of V2 with V4, I get BC. Now the question is AB a subset of BC, or is BC a subset of AB? And the answer is no. So the question is, do we have a high-level data race? Well, we don't have the program here, so we don't have the dependency graph to know whether they have this common or relation or not. But if they do, then it's a high-level data race. If they don't, then it's not. Deadlocks. Questions up to now? I told you I can speak for 2 hours without stopping. I told you. So deadlocks. What are deadlocks? Well, this is a classical example with deadlocks. You get to a crossing. This is a shared space that has to be used somehow in more or less exclusive way. And you have 4 cars approaching, and then the drivers, all of them go to the crossing space at the same time. And we say, oh, bullshit, no one does that. Oh, they do. So things happen. So yeah, there are deadlocks in real life as well. So how to handle deadlocks? How to understand deadlocks? First of all, let's see the system model. We have a finite number of resources, and the resources are organized into classes. And when I request a resource, actually I say, I want any resource of that class. It's easy to explain with printers. If I may have a class which is the black and white printers, and I may have 3 of them, and I have another class which is the color printers, where I have 2 of them. And when I want to print something, I just want to say, I want to print it black and white, or I want to print it color. I don't care in which of the printers the output is going. If they are all nearby each other, if they are one here and another one in the other building, then I care. So then they are not in the same. They are not in the same class, in the same set. So when I say that I have multiple resources in the same class, I mean that the client, the one that is asking for the resource, will be happy with any of those resources. If for some reason he's not happy with this condition is not valid and he prefers one resource to the others, then they are not in the same class. So when the same class means any resource is valid and will satisfy the client. Now, the client obeys this protocol of request the resource, use the resource, release the resource. With locks, for example. Lock, use, unlock. And this is very common. We see this without locks in our world with malloc, to get memory, use memory, release memory. Open file, use file, release file. So this protocol is common even without locks. The problem with locks and that drives you to deadlocks is that these deadlocks have this semantics of if lock is being used, you have to wait for it to be released. And then it can drive you to deadlocks. All right. So what are the conditions for a deadlock? You have you have 2 or more processes involved. It's impossible to have a deadlock with just one, supposedly. But you have 2 or more processes involved. And they are all blocks. So they're not running, they're not progressing. Because if they're progressing, trying and going back, it's a live lock, it's not a deadlock. So they're stopped, blocks. And each one is holding at least one resource. And each one is waiting for a resource that is being held by one of the others. So, yes? You may have a deadlock and not all of the process being involved, but we say they are involved in a deadlock if this is true. You may have other processes that are not involved in this deadlock process. Yep. So, but because the specification here is a set of 2 or more processes are deadlocked if. I'm not saying anything about the processes that are not deadlocked. So the program itself as a whole may have some progress in the other threads, but I'm not speaking about the threads that are progressing. I'm speaking about the threads or the processes that are being involved in the deadlock. And this is a sufficient condition for this. And now, what does it mean? Basically, it means that I have two processes and I have two resources, and basically this process has access to one resource and get it. And then this process has access to this resource and get it. And now the first P1 has access to P2, to resource 2, and say, oh, I have to wait. And then P2 does the same for R1 and has to wait, and we have a deadlock, basically. So, deadlock depends on the dynamic of the execution. Because here I have a deadlock, but it's also possible to run the program and the deadlock does not show up. Because if this one asks for resource 1 and for resource 2 before this one asks for resource 2, then there is no deadlock. Or the same here, if this one asks for 2 and then for 1 before this one starts and asks for 1, there is no deadlock. So again, deadlock the deadlock does not have to happen in all the runs, and some runs may have a deadlock error, some other runs may go all right. So, what are the conditions, necessary conditions to have a deadlock? Necessary, not sufficient. Well, we have to be using some kind of multi-wall exclusion with locks or semaphores or something like this with the usual semantics. You have to wait. And you have to have this hold and wait, which means a process holding at least one resource is waiting to acquire a lock or to acquire the additional resource that is being held by someone else. But I'm holding it, so I have one and I don't release it, and I'm waiting for the other for something else, but I keep mine. So that's what hold and wait means. And also no preemption, which means a resource can only be released by the owner's will. So I cannot go and force and take the resource out of some other process. And finally, I have to have this circular wait of P1 waiting for P2, for P3, for P4, for P5, that goes back to P1. Or P0 if we start counting on 0 instead of 1. So, and these are sufficient conditions. They are not necessary, sorry, these are necessary conditions, not sufficient. So all of them may be true, and we still don't have a deadlock. So, let's see this example. Thread 1. I'm locking M1, M2, do something, unlock. Thread 2, lock M2, M1, do something, unlock. And can I get a deadlock here? And the answer is obviously yes. Will I always get a deadlock? And the answer is, I hope, obviously not. So, if we number the operations 1, 2, 3, 4, basically, I get deadlocks with interleavings 1, 3, 2, 4, 1, 3, 4, 2, 3, 1, 2, 4, and 3, 1, 4, 2. But if I get 1, 2, 3, 4, or 3, 4, 1, 2, then there is no deadlock. Basically, if this runs first and this runs afterwards, or vice versa, I don't have a deadlock. If they mix, then I have a deadlock. Which means, again, that detecting deadlocks is sensitive to the overage, if you are trying to detect them this way. So how do we handle with deadlocks? Well, how do we work for detecting deadlocks? We do this resource graph analysis. And resource graph analysis means we have vertices and edges, and vertices represent both processes and resources, and edges may be request edge or assignment edge. And let's represent them visually, processes and resources. And this is the resource class with 4 instances inside. And then this is a request of a process to a resource, so an arrow from process to the resource means a request. And I request an instance of this class. So the request goes to the class because any of the instances, any of the resources that are part of this class are okay for me. And this is the assignment, and the assignment is a particular resource is assigned to the process. So the other 3 resources are free here. So if I have a situation like this, where I have process 1 requesting this resource, which is being held by process 2, which is requesting this resource, which is being held by process 1. Do I have a deadlock? Guys, do I have a deadlock? Yeah, I do have a deadlock. Thank you for the enthusiastic participation. And what about this one? What's the difference? I have two, each class has 2 instances, 2 objects inside instead of just one. Do I have a deadlock? The question is, this resource is being held by this one, and this one is requesting an instance of this resource. Will it get it? I have 2 free, yes. So it will not wait for this one, because I have 2 free instances of this resource, and I'm requesting just one. And the same down here. So this one is safe. So having this circular dependency is a necessary condition, but it's not enough. All right, it's not sufficient. I may have all those properties verified, and still I don't have a deadlock. So the question is, oh, this one. Do I have a deadlock? Do I have a deadlock? Do you vote for the Prime Minister? Or in the elections? You do. Come on, do I have a deadlock? Yeah, I do. Do I have a deadlock? Oh, I have no idea. Do I have this circular problem? Yes, I do. All the resources are being held? Yes, it looks like I have a deadlock. Right? But the thing is, R2 doesn't have any other request edge. P2, neither P4. So eventually, they will stop. They will finish, and they will release the resource. And then they will release the resource. This one that is requesting will get the resource. All right? So the thing is, it's safe. Because both when P2 finishes or P4 finishes, these threads will progress. This process will progress. So it's safe. Yes? Yes, sure. I'm making the assumption that programs are well behaved. We have bugs, but programs are well behaved. If they don't terminate, that's one of the problems with lot programming. If a thread, this is one of the problems with you if you use lot programming. If a thread terminates, you are done without releasing the lot. Yeah, but again, if the program is running forever and acquires a lot and never releases the lot, you assume that in the system model, I was assuming request, use, release. And I'm assuming that the processes follow this model. If the processes don't follow this model, either because they die before they release, or they just don't release because they are bad behaved, then this model doesn't apply anymore. All right? So what I'm telling you here is not, you have different situations. I'm assuming that the programs are well behaved in the sense that they follow the specification, they require the law, or they use the law, they use the data, and then they release the law. So, basic facts. If the graph contains no cycles, no deadlocks. If the graph contains a cycle, maybe there is a deadlock. Interesting fact, if there is just one instance, one resource per class, if there is a cycle, there is a deadlock. If I have more than one resource per cycle, per class, if there is a cycle, I may or may not have a deadlock. How do I handle this? How do I handle deadlocks? Well, I can do, first of all, deadlock prevention and deadlock avoidance. These are 2 strategies that don't allow the system to go into deadlock state. Neither of them. And then I have deadlock recovery. The system goes into a deadlock state, and I recover from the deadlock state. And I can also ignore the issue. And I have to tell you that ignoring the issue is a popular solution. It happens a lot in operating systems, for example. The probability of having the deadlock there is so low, so low, so low, so low that they just leave it there. But it happens. So ignoring the issue is a solution sometimes. Depends on whether your software is critical or not, right? If software is critical, you don't want to ignore the issue for sure. If it is not critical and probability is 0.0000000000000, many zeros, one, it's just on error. So it's possible. So let's go very quickly, because I'm running out of time, about deadlock prevention. Deadlock prevention, basically, the idea is you have these 4 properties that I told you that are necessary properties to have a deadlock. So if you basically break one of them, your system will never go into deadlock, because they are necessary conditions. You just have to break one of them. And how do you break them? Let's go one by one quickly. Mutual exclusion. The thing is, request less lots. And use read lots and write lots, because read lots can be shared. So you have a lower probability of having deadlocks, because read lots are compatible with each other, and so you have you are allowing more interleavings, more current operations, so the probability of deadlock is lower. Does it solve it completely? No. It's just a way of reducing the probability of having a deadlock. Then, hold and wait. How do you do this? How do you solve this? Hold and wait means I have a resource, and then I will ask for another resource, and I'm waiting for it. So the thing is, well, you can specify this protocol that instead of asking the resources one by one, you say, I want all of these resources. And it just returns when you get all of them. So you get all or none. So you never get to this hold one and wait for others. Basically, you ask all of them in the very beginning, and you get all of them or none of them. And how do you handle this non-preemption? Sorry. So if the resources, if a process is holding some resource and then requests some other, it is either immediately allocated or the resources it has are released, and it tries again. Basically, no preemption means I will not keep my resources forever. So I have some, and now I will ask for another one. And if I can get it, great. If I cannot get it, I will release the one I already have. So, and I will restart from the very beginning. So it's a way to also break the hold and wait. And finally, the circular wait. How do I handle this? Well, if I get to the circular state, this means I can somehow roll back one of the processes. I have to roll back one of the processes and set it to a state before acquiring the lock, releasing the lock, set it back, and restart again. So these are different solutions with different approaches to avoid deadlocks. So that was deadlock prevention. Deadlock avoidance. What do we understand by deadlock avoidance? Well, it's a different strategy, basically. But basically, each process declares the maximum number of resources that it needs, basically. So you need a set of resources, and you declare it in the very beginning. And then basically you acquire these resources, and these resources are sorted somehow, and you acquire them by order. And if you do this in a very polite way, you don't get deadlocks. What's the problem here? You have to know in the very beginning all the resources that you need, and sometimes you don't know all of them. And so this doesn't apply always. It's not possible always to apply this methodology. So I will go quickly. But basically, what these two approaches do is you have the set of safe states in a program, and you have the set of unsafe states in a program. And deadlocks are a subset of unsafe states. So if somehow you force your program to always be here, in this area, you will never get there. If you allow your program to go to this area, sometimes you may get into this situation. If you are here, you are still not in a deadlock, but if you move there, you are in a deadlock. So let's go here, and let's speak just about something, which is, yes, 5 minutes, yes. Let's go very quickly speak about the banker's algorithm, just for you to know. what I've been telling you, or these strategies work very well if we have just one resource per class. If we have multiple resources per class, there is this very nice, interesting algorithm named Maker's algorithm, which I'm not sure whether it was Lamport who proposed it as well. And it really works with any number of resources per class, with any number of classes, and it's a very general algorithm. So deadlock detection, if you go to deadlock detection, what do you have? Basically, it happens is you get into deadlock and then you re-over from it. And when you speak about re-overing from deadlocks, basically you build these dependency graphs as well, but the system, instead of avoiding the system to go into deadlock, because sometimes if we go here, if we are doing, sorry, where is it? If we are doing deadlock prevention, we are forcing the program to be here. If we are doing deadlock re-overing, we are allowing the program to go here, and even to go here. And just when it gets here, we re-over from the state. So we allow more computations. So the program is free to do more computations than it is if we stay here in this world. So basically, when we go to deadlock detection, we are allowing the program to go on the full space, and when it gets to this supposedly small set of really deadlock states, we re-over from this state. And how do we do it? Basically, we have to take the program from one of the threads or one of the processes from the deadlock state. Is it possible? Well, sorry, let's go here. Strategies. Abort all deadlock processes. Preempt some resources. Roll back each deadlock process. And these are different strategies that allow me to re-over from deadlocks. And the strategies that, when I decide what to do, for example, if I decide to restart some process, it's not clear what I should do. Which process should I start? Restart. Should I consider priority? Or should I consider how long it has been computing? Because if it has been computing for a long time, maybe let it finish. Or how much does it has to go until it completes? Or the number of resources that is holding, or whatever. So there are multiple criteria, and it's not obvious which one is the best. So, selecting a victim, we will always want to minimize host, whatever is the host function. Then we roll back. And this, although it's nice, we have this problem of starvation, because when the process goes again, it may get again into deadlock, and it may be selected again as a victim, and it restarts and gets again into deadlock, again as a victim. So this deadlock re-overy has this strategy, has this problem of starvation. We have to handle it. Finally, a variation of Maker's algorithm can also be applied here. I will skip the Maker's algorithm because I'm running out of time. But with these tables, you can get there. And yep, finally, some acknowledgements for some credits for people that somehow contributed to my slides that I found publicly somewhere, and I found them nice, some of them. And that's all, folks. And before you go away, because, oh, I'm hiring as well. So, less than a month ago, I was notified that I had a new research project approved. So it's going to start next month, as I hope. The name is Hipster, High Performance Transactions. And basically the idea is to work with this dilemma between improving the efficiency of resilient systems, fault-tolerant systems, while keeping them correct and easy to use. This is the global motivation for the project. And the important keywords are not verification here. The important keywords are these ones: fault tolerance, replication, performance, and transactions. Yes, transactions are very important here. So basically, I have a 2.5 years contract that may start soon. So if any of you are finishing your PhD or did it and wants to consider coming to Portugal, Lisbon, we have beach and sun. We don't have snow, but we have beach and sun. Yes. Why? You have ice and snow and skiing. Sorry.